We are on page 6 of the student note packet. We're going to finish up examples on pages 6 and 7. Then your homework is located at the bottom of page 7. You guys are going to do your homework the same way that we do the examples in this lecture, so ignore the book directions and follow the examples that we're doing in the lecture today. Okay, so we're getting into the third day of vectors. We have discussed how to add vectors using the parallelogram method. That's when we have two vectors and the angle between them, and then also the tail to head method, generally when we're like mapping a trip and we're trying to find the net distance traveled. Today is that third way that we can sum vectors, and this works given various circumstances or pieces of information. We're going to talk about horizontal and vertical components for vectors today. So more things on vectors. Vectors can behave like real numbers. They can be added and subtracted. We know that. They can be multiplied by a scalar, so some constant or real number that can enlarge the vector, essentially changing its magnitude. We can do that looking like this. V plus V, that's the same thing as 2V. That's scalar, then is 2. So when we change a vector by multiplying it by its scalar, just note that the magnitude of that vector also changes. And sometimes if that scalar is negative, the magnitude can also, not only the magnitude can change, but also the direction. So today we're talking about horizontal and vertical components, and we're going to talk about the unit vector. That's important in this one. So the unit vector is any vector that has a magnitude of 1. We call the special unit vectors I and J. I represents a unit vector in the x direction or the horizontal direction, and J is our unit vector in the y direction, so the vertical direction, up and down. If I have this vector 3i or negative 8j, what we're talking about here with 3i is a vector that is 3 units long, has a direction of 0 degrees if we're still using the unit circle. Okay, so 0 degrees like on the positive x-axis. Negative 8j then would be a vector that is 8 units long with a direction of theta is equal to 270 degrees. So that's straight down along the negative y-axis. Again, when we use theta, we're talking about unit circle measures. So a way we can write these, xi or yj, these are any I or j vectors, those unit vectors that have both a direction and a magnitude. That direction is implied by that unit vector I or j. So I and j give us the direction. The magnitude is the scalar. So in this case, it'd be that x or the y, the number in front of vector I or vector j. Every vector can be written as a sum of its horizontal and vertical components. So let's say we have this vector v here that I've graphed in red. We can break vector v into its horizontal and vertical components by essentially creating a right triangle with the x-axis and then figuring out what the horizontal and vertical components are. So this vector goes 1, 2, 3, 4, 5 units along the positive x-axis, or 5 units along the horizontal. So we can break vector v into its horizontal components by saying 5i. So you'll see me write it with like a hat like that, but it's the same thing if you do the vector like that. And then the vertical component then is 1, 2, 3 up. So plus 3j. And it's positive 3 because it's up 3. It's positive 5 because it's to the right 5. If we had gone left and down, we'd be negative 5 and negative 3. But there is vector v written as its sum, the sum of its horizontal and vertical components. Okay, so for the first set of examples here on page 6, we have an initial point P and a terminal point Q identified here by our examples. What we want to do is we want to sketch the graph of this vector, and then we want to write the vector as its sum of horizontal and vertical components. So imagine we've got a set of axes here, and if our initial point P is at the origin, it's at 0, 0, and Q is at negative 5, 12, negative 5, 12 is going to put us in the second quadrant, somewhere like this. Now remember, we're drawing vectors here, so we need a tail and we need a head. The head is going to be at our terminal point Q. And what do I know about these 2 points? Well, this is negative 5 and this is 12. We went left 5 and up 12 from P to Q. So the vector PQ You can write it like that, as its sum of horizontal and vertical components is going to be negative 5i plus 12j. We just write it exactly like that. For number 2, P and Q, different places. So here in this case, we don't start at the origin, makes it a little bit more difficult. P starts at negative 8, 3. So negative 8, 3 is going to be somewhere over here in the second quadrant. And the terminal point, Q, is going to be 2, negative 4. So 2, negative 4 is going to put us in the fourth quadrant. Again, because that's our terminal point, when I draw the vector here, the tail is at point P, the head of this vector is at point Q. All right, so again, if I were to sketch a right triangle here between these 2 points, we're looking for the horizontal and vertical components here. So from P to Q, and the direction is really, really important. We're going from P to Q. So that means, let's talk about horizontal first. Along the horizontal from P to Q, we're moving right, which means our horizontal component is going to be positive. So how far to the right? Well, if we start at negative 8 along the x-axis, we're walking all the way to 2. So imagine walking along a number line. I'm starting at negative 8, I'm going to 2. We're walking a total of 10 steps. So we're 10 along the horizontal. Now vertically, from P to Q, we have to move down. So the vertical components here must be negative to get from P to Q. Now how negative? Well, at P, we're starting up at 3, and we're going all the way down to negative 4 along the vertical or along the y-axis. So if we start at 3 to get to negative 4, we have to go down 7. So we represent that movement down using a negative value. So vector PQ here is positive 10 in the horizontal direction, so 10i minus 7j. Pause the video, try number 3, and then I'll have the answer for you. Number 3, sketch looks like that. From P to Q, we are going left and down, which means both of the components are going to be negative, negative 4i minus 7j. Okay, so now we have these horizontal and vertical components. We now have 2 forms for defining a vector. So the first way we can do is what we have been focusing on the last 2 lectures, magnitude and direction. So the length of the vector, the direction that it's facing. The second option then is just the horizontal and vertical components, because splitting things into its horizontal and vertical components get us a way to get the magnitude and the direction. That's what we're going to figure out how to go between now. So let's start by giving the magnitude and the direction, how we break this vector into its horizontal and vertical components. So as always, I'm going to start by just sketching this vector. We're using theta, so we're using unit circle angles here. Okay, so 300 degrees, starting on the positive x-axis, going counterclockwise, gets us just 60 degrees shy of a full circle. Okay, so that's our 300 degrees right there. Don't confuse this direction with bearing. And what do I know? Well, we also know the magnitude here is 11. So here's the deal. If we were to create a right triangle with the x-axis here, I know this angle is 60 degrees. And the hypotenuse of this triangle then is the magnitude of our vector. It's 11. So this is a 30, 60, 90 triangle. We know a couple of things about 30, 60, 90s. I know that the short side of a 30, 60, 90 is half the length of the hypotenuse. So the short side is 11 over 2. And then the longer side is just the short side times the square root of 3. So the longer side is 11 root 3 over 2. Now, we're down in the fourth quadrant, so that y value there needs to be negative. But there are the vertical and horizontal components for this vector A. Horizontally, we go right 11 over 2. So 11 over 2 I hat, that's the first horizontal component. And then the vertical component, minus 11 root 3 over 2 j hat. That's it. Right 11 over 2 and down 11 root 3 over 2. All right, let's try one more. We have this vector V in example 5. its magnitude is 10, its direction is 225 degrees. Again, not bearing, we're using unit circle values here. So 225 degrees is just right in the middle of the third quadrant. Looks something like that. Remember, we need a tail and a head on our vectors. The magnitude here is 10, and if I make a right triangle with the x-axis, I know this angle in here is 45 degrees. So we have a 45, 45, 90. And we have the hypotenuse of this right triangle. So what do we know about the hypotenuse and the sides of a 45, 45? Well, the sides are the same. And we always take the side and multiply it by the square root of 2 in order to get to the hypotenuse. So to go backwards, we're going to divide by the square root of 2. Now, we're in the third quadrant, which means the horizontal and the vertical components are negative, and we are definitely not going to leave our final answer as negative 10 over the square root of 2. We need to rationalize that. Okay, so just kind of on the side, negative 10 over the square root of 2. To rationalize, I'm going to multiply by root 2 over root 2. That gives me negative 10 root 2 over 2, which is negative 5 root 2. Okay, so the horizontal and vertical components for this vector are left, root 5 over 2, and down, root 5 over 2. So negative 5 root 2 I hat minus 5 root 2 j hat. Pause the video, try number 6, and then come back for the answer. All right, there we go. When our magnitude is 13, theta is 150, which leaves us with another 30, 60, 90. The horizontal and vertical components then are negative 13 root 3 over 2 I hat plus 13 over 2 j hat. Okay, so with the last 3 examples, 4, 5, and 6, we got a little bit lucky. We had really nice angles. So we had unit circle angles that gave us 30, 60, 90 degree triangles or 45, 45, 90 triangles of special right triangles. But what happens when we're given something that is not easy? So an angle like 143 degrees that is definitely not on the unit circle. We have to approach it a little bit differently. So let's actually draw this, and then we'll see what we're looking at for horizontal and vertical components. If theta is 143 degrees, then our vector A is going to sit in the second quadrant, just a little bit more than halfway through that second quadrant. All right, the magnitude of that vector is 3, which means the length is 3. This is that 143 degrees. So I also know the inside angle there. It's just 180 minus 143. This angle here is 37 degrees. Okay, but again, small problem. 37 degrees does not make a special right triangle. So we have to use some other things in order to help us evaluate what those horizontal and vertical components are, and I'll call them X and Y for now. Okay, so we have something that's really nice. We actually can use right triangle trig. We can use SOHCAHTOA here in order to help us figure out what X and Y are. So if I want to solve for Y first, we have the angle 37 degrees. We have the side opposite and the hypotenuse. So I can say that the sine of 37 degrees is equal to y over 3. And then similarly, I can say the cosine of 37 degrees is equal to x over 3. All right, so x is equal to 3 times the cosine of 37. Y is equal to 3 times the sine of 37. But there's a small problem here. When we do it this way and we use the cosine of 37 degrees, both of those values become positive. We type that into a calculator. We know our angle sits in the second quadrant, which means the x value here, that horizontal component, must be negative. So you can use 37 degrees. You just have to be careful to make sure that your sines match the quadrant that you're sitting in. But the other thing we can do is we can use that 143 degrees. And if we use 143 degrees, what happens is we get the sine right every single time. So I can also say that the sine of 143 degrees is equal to y over 3, which means y is equal to 3 times the sine of 143. And this cosine of 143 degrees is equal to x over 3. So x is 3 times the cosine of 143. when I type these things into my calculator, 3 times the sine of 143 is something like 1.81. And 3 times the cosine of 143 is negative 2.3 or 40. Okay, so when we use 143 degrees, we actually get the right sign. In any case, the sum of horizontal and vertical components here is going to look like this. Negative 2.40 in the horizontal plus 1.81 in the vertical. So negative 2.40 I hat plus 1.81 j hat. So we just did 4, 5, 6, and 7. 7 obviously was a little bit more complicated, but 7 kind of leads us to a generalized formula for allowing us to resolve something into its horizontal and vertical components relatively quickly. So anytime we've got a vector, if we just take the magnitude of the vector, we multiply it by the cosine of its angle in standard position, so that's using the unit circle value, and then add the magnitude times the sine of the angle in standard position for the vertical components, we end up with this general formula. Magnitude cosine I hat plus magnitude sine j hat gives us the horizontal and vertical components pretty immediately. Now, we're going to make one kind of note here. That theta value has to be in standard position. That is unit circle angle. So if you're given bearing, you have to convert the bearing into standard position first. Okay, so let's use that general formula here. We are lucky in these examples because we are already given the angle in standard position. Let's sketch this vector and then find its horizontal and vertical components here. So 307 degrees is sitting in the 4th quadrant somewhere. And this vector has a magnitude of 19. Well, we have a really quick way to get this into horizontal and vertical components. That is going to be 19 times the cosine of 307 I hat plus 19 times the sine of 307 j hat. And then you just type that into a calculator. We'll round to 2 decimal places here. So 11.43 I hat minus 15.17 j hat. And again, if you use the full theta, you never have to worry about your signs. It'll always work out that way. Great. Pause the video, try number 9, and come back for the answer. There we go. Magnitude is 21. Theta is 199. We're in the 3rd quadrant, so sketching it just kind of gives us a way to really quickly mentally check the, or visually check the signs. Both horizontal and vertical components need to be negative, and that's what we get. Okay, so this is where we start to change things up. Instead of magnitude and direction, what happens if we're given horizontal and vertical components? We want to turn those into a magnitude and a direction. Well, the first thing we're going to do is we're going to graph the vector, and then we're going to see what happens here. So when I graph this vector is defined negative 8 in the horizontal and positive 8 in the vertical. So we go left 8 and up 8. It's going to create a perfect 45-degree angle there. Okay, so there's our vector V. And there's a couple things I know. We went to the left 8 and up 8 to get from the origin to our terminal point. And if we're asked to find the magnitude and the direction, what we want is we want the length of that vector, so essentially the hypotenuse of this right triangle, and this value theta here. Okay, that's the direction we're looking for. Now, a couple things. The sides here are the same in this right triangle, which means this is a 45, 45, 90-degree triangle. So really quickly, the magnitude of this vector, remember we write magnitude inside absolute values, that's just 8 root 2 from 45, 45, 90. You could also use Pythagorean theorem there. And then also, we can also quickly solve for theta. That's just 180 minus 45, or 135 degrees. There you go, magnitude and direction. Same thing here for number 11. We have our vector V, so defined by 7i minus 24j. We're going to sketch it first, and then we're going to figure out its magnitude and its direction. So 7 and negative 24. That's like graphing the point 7, negative 24. We're going to go right 7 and down 24. We're going to have a pretty steep incline here, right? Something like that. and that's our vector v. We want to find its magnitude and its direction. So we need to find the length of that hypotenuse when both of those sides are 7 and negative 24. And then the direction, we're going to start on the positive x-axis, go counterclockwise. We're looking for that angle theta there. Now, these aren't necessarily nice angles we're looking for, so we're going to use Pythagorean theorem to first find the magnitude of this vector. So Pythagorean theorem says a squared plus b squared is equal to c squared, our hypotenuse. So v squared is equal to 7 squared plus negative 24 squared. The magnitude of this vector, then I'm just going to type this into the calculator. Looks like 25. That might be that is a Pythagorean triple. So if you didn't know it, Pythagorean theorem works for you. Okay, so what we don't have though is the bearing, or sorry, the direction here. A couple of things that you can do. I'm just going to find this little angle on the inside. I know that the tangent of alpha is equal to the side opposite over the side adjacent. Now, if I keep that negative 24, what happens is I'm going to end up with a negative angle, which is fine. But also, when we do it this way, when we're finding the angles on the inside of the triangles, I can also just use the values without the signs and kind of work backwards from there, which is what I prefer to do. Okay, so alpha is equal to the inverse tangent of 24 over 7. That is 73.74-ish degrees. All right, so theta then, what we're actually looking for, the direction of our vector is just 360 minus alpha. So 360 minus that is going to be 286.26 degrees. There's our magnitude and our direction. All right, number 12 is all yours. Pause the video, and then when you're ready, come back for the answer. Vector v, down in the third quadrant, both horizontal vertical components are negative. I use Pythagorean theorem here to help us find the hypotenuse. Can't simplify it other than the square root of 41. And then I use tangent or inverse tangent to find the angle on the inside of the triangle, and then add that to 180 to get the total direction. All right, last two examples here. Number 13, we've got some word problems to practice. Max the dog takes his pet Jennifer the pony for a walk. He pulls Jennifer eastward. So eastward is going to be to the right in a wagon with a force of 63 pounds. The handle of the wagon makes an angle of 27 degrees with the ground. We want to write the force factor as a sum of its horizontal and vertical components. Okay, so here's what's happening. Jennifer's in a wagon, and Max is pulling the handle of the wagon with a force of 63 pounds. So I'm going to essentially, and we're going eastward, which means we're going to the right. Okay, let's imagine that this is the handle of our wagon. And then the wagon's like over here, right? With our pet pony in it. There you go. That's it. Good. Okay, what are we told? The force applied on the handle is 63 pounds. That's how you abbreviate pounds. And then we also have an angle of 27 degrees with the ground. So if I go straight horizontal here, that's the ground, right? Or parallel to the ground. That's 27 degrees. Okay, those are things that we know. If I make a right triangle here, what we're looking for are the horizontal and vertical components, the x and the y values. So I can, in this system, set my origin at the place where the handle and the wagon meet. And then we can use the general form for finding the horizontal and vertical components of our vector. That's just the cosine, or our magnitude times the cosine of our angle in standard position, plus the magnitude times the sine of our angle in standard position. I'm just going to type those things into a calculator and get the answer. So the hardest thing about the word problems is just trying to figure out what it's asking and then set it up so everything makes sense. There we go. 56.13 I hat plus 28.60 j hat. Okay, last thing here. We have two forces. One has a magnitude of 53 newtons and the other has a magnitude of 47 newtons. They both act on an object at angles of 122 degrees and negative 114 degrees with the positive x-axis. We want to find the direction of the magnitude of the resultant force. Now, if we look at this problem the way that it is, we have enough information to find the angle between them. And then if we have two vectors and the angle between them, we know that one option to sum these two vectors together is that parallelogram method. I create that parallelogram, find the diagonal, and that's the sum of the two vectors. That is one option. Today we're going to focus, though, on using horizontal and vertical components to actually sum two vectors together. So what we're going to do is we're going to express each of these vectors as their horizontal and vertical components. And then what we can do is we can add the horizontal and vertical components together so that they're, the two vectors added together get us the resultant vector, which would have been the diagonal of the parallelogram if we use that method. Okay, so let's start with this first vector, the one with 53 newtons of force. That has an angle of 122 degrees. So 122 degrees, we're good. That is in standard position. And technically so is negative 114. We know it's standard position because they're measured from the positive x-axis here. So I'm going to call this force 1. And we can represent force 1 as its horizontal and vertical components by taking its magnitude, multiplying it by the cosine of its angle in standard position, and then its magnitude times the sine of its angle in standard position. Okay, so similarly then, the second force down here, I'm going to call this force 2. Same thing. Magnitude times the cosine of the angle in standard position plus magnitude times the sine of the angle in standard position. Negative 114 degrees is an angle in standard position. We can have negative angles. That's fine. You can type in the cosine of negative 114. If you don't like negative angles, if you just do 360 minus 114, we get 246 degrees as the positive. Doesn't matter. Both answers are going to get you the same place in your calculator. Now, we are ultimately summing these two forces to get the third force, which is the sum of the first two. So instead of writing it as F3, I can write it as F1 plus F2. Right. And all we're going to do is we're just going to add like terms. So we can add all the forces in the horizontal direction because they have the same like variable, if you want to say, that I hat. And we're just going to do it in a calculator. 53 times the cosine of 122 plus 47 times the cosine of negative 114. That is negative 47.20 I hat. And then I can do the same thing for the forces in the vertical direction. 53 times the sine of 122 plus 47 times the sine of negative 114. That gives me 2.01. Okay, that is the vector, the resultant vector from adding these two forces together. We're not complete here though. What we're asked to do is we're actually asked to find the direction and the magnitude of that resultant force. We have that force as a sum of its horizontal and vertical components. So now what we have becomes a problem then like numbers 10, 11, or 12. We have this vector with its sum of its horizontal and vertical components. We can find its magnitude and direction now. So we can either graph this vector on the same system that we have the other two, the same diagram, or sometimes I like to just do it on its own. So if I were to graph F1 plus F2 here, right, negative 47.2 and then 2.01, that is like something really, really, really close to the x-axis going in the second quadrant, where, and obviously this isn't quite to scale, this is negative 47.02, and that is the 2.01, the height of that triangle that gets made there. What we're asked to do is we're asked to find the magnitude here, so the length of the hypotenuse essentially, and the direction, so that angle theta. That's our final answer. Okay, so we're going to use Pythagorean theorem in order to figure out the magnitude here. So the hypotenuse squared is equal to negative 47.02 squared plus 2.01 squared. Don't forget to take the square root when you're actually solving for the final magnitude. Okay, type this all into the calculator. I'm getting something like 47.25 newtons. That's the unit we're in. We're talking about force. Okay, so there is the magnitude. The sum of the two vectors is a force that is 47.25 newtons. And then the last thing we need is the direction here. So different ways you guys can go about doing it. We have a right triangle. I'm going to use the tangent here, and I'm going to solve for this angle on the inside. So the tangent of alpha is equal to opposite over adjacent, and I'm just going to use the positive value here and then kind of work it out. So alpha is equal to the inverse tangent of all of that. Getting a really, really small number, right? 2.44 degrees. And that kind of lines up with what we know about something that is so long along the x-axis, but really, really short along the y. So 2.44 is alpha. So our actual direction here is just going to be 180 minus that. That is looking like 177.56 degrees. Okay, a little bit longer sometimes using horizontal and vertical components to add two vectors together and then find the magnitude and the direction. Over the parallelogram method. The parallelogram method can get us to that magnitude really quickly, but it's that direction that gets a little trickier. So we have all three methods of summing vectors now: parallelogram, tail to head, and horizontal and vertical components. And now we can start applying each of those methods to various word problems to help us kind of find the information that we need.